Hello friends, we will start with a new module now. Okay, we have already seen the constitutive equations. The next module is on the processing maps. Okay, so for a practicing engineer who is on the shop floor, who is actually looking after the production. Okay, if I tell him all about this dynamic recrystallization, dynamic recovery, the flow stress. Okay, if it looks like this. And this will be the mechanism. Okay, and in this temperature range or strain rate you have to do the deformation or the processing. He will not enjoy this particular idea, okay, that you are coming with all this flow stress, because he has to look after the production. Okay, he does not have time for all these niceties and your enthusiasm for dynamic recrystallization, dynamic recovery. Okay, he wants to have a very clear answer that if he is designing a process, okay, which temperature, strain rate he should be working in, what will be the flow stresses, okay, and which are the region where he will be able to get a good processing. Okay, that means you will have maybe a recrystallized microstructure, that is what we usually like to have, and which regions to avoid. Okay, maybe in some regions you will be getting there may be some crack formation or some other defects which are going to come or which are going to be present in the material. Okay, so which regions to avoid, okay, and which regions are the regions to for the processing. Okay, so you must have seen at large number of places we use these kind of maps to clearly bring out and in engineering, okay, practice where engineers do practice, okay, actually do the work. Okay, they want to have this kind of maps where clearly you can demarcate, okay, this is my processing region. Okay, and usually all like graphical means are always better. For example, in our stress analysis also we use Mohr circle, okay, because a graphical representation very quickly bring out the main idea behind a particular aspect. For example, in a stress analysis, or as we are saying in case of processing maps. Okay, so these maps are very convenient for a practicing engineer to identify the processing conditions. Okay, now as I was trying to tell you that what regions to do the processing and what regions to avoid. Okay, if you look at any plastic deformation or during a hot deformation or thermomechanical processing, okay, the main our main objective is that I should be able to deform it without any difficulty, and I should be able to avoid any failure which in the material. Okay, there should not be any defects in the material. So this is what we call as workability, that I should be able to work on my material. Okay, so their workability also can be kind of defined in two ways. Okay, one is called extrinsic workability, which depends on the state of stress. Okay, that whether it is a uniaxial deformation, it is biaxial deformation, it is plane strain deformation. Okay, so what kind of deformation it is, okay, whether it is a shear deformation. Okay, so one workability depends on that, okay, whether it is triaxial deformation. So severity of the deformation increases as you go from uniaxial to biaxial to triaxial. Okay, and of course you can also have more chances of introducing defects. Okay, whereas in shear process you can go to very high strains without introducing defects. Okay, for example, surface cracks and so on. Okay, whereas in compression you can easily introduce surface cracks if you are doing a large deformation. So this is the extrinsic workability of the material, which depends on the state of stress. Okay, what type of stress system is there, plane strain, plane stress, compression, shear and so on. Okay. The intrinsic workability is the inherent characteristic of a material, okay, and that depends of course on the constitutive behavior of material, that what is the material's response to in terms of flow stress its response as a function of strain, strain rate and temperature. So, that is the intrinsic workability, that is of course material specific property, okay, that how material behaves under a certain set of conditions, okay, and that will be intimately related with the deformation processes which takes place during this deformation, okay, at particular deformation conditions. So, the response, the flow stress response can be then also looked as the microstructural response, okay, that what will be the response of the material. So, microstructural response also we can segregate the response in two categories. One is what we desire, okay, and one which is undesirable. Okay. So, dynamic recrystallization, dynamic recovery, these type of microstructural response is desirable, okay, because it gives it enhances the workability of the material. You are able to deform the material, as you can see as in dynamic recovery, dynamic recrystallization, you if you reach the steady state, okay, there is no change in the flow stress as a function of a strain. So, it is a steady state condition, you are able to deform to larger strains, okay, ductility will be more. Okay. So, this particular region we want to work in. Okay. Undesirable microstructural response are the introduction of defects. Okay. So, damage, instability like adiabatic shear bands, cavitation, cracking, okay. This we should not, we do not want in the material, because if crack is there in the material or cavity is there in the material, it will bring down the strength of the material. Okay. As you know, in fracture mechanics, a crack, if a crack is there, it when I am applying any tensile stress, it will start propagating and your material will fail after some time. Okay. So, there will always be a problem of failure of material if you have any defects in the material. So, again as we were discussing in the constitutive equation, that the constitutive equation idea started from the creep deformation, okay, and creep already I have told you the creep is a very slow deformation as a function of time, okay, time dependent deformation, okay, in which the strain rate of deformation is very low, 10 to the power minus 8 to I think 10 to the power minus 5, that is the window we decided for creep. Okay, just to kind of recap it, that is the strain rate we reach, okay, and creep is basically your time dependent deformation. Okay. And in this case actually you do not apply the strain rate, but you apply a constant load. Okay. So, you apply a constant load or you can say stress, okay, and the material response is seen in form of strain rate. Okay. So, slightly different than the hot deformation processes, where you apply strain rate and you see the material response in form of stress. Here we apply a constant load or stress and we see the material response in terms of strain rate, okay, that how fast the strain is being accumulated in the material as a function of time. Okay. So, constitutive equation also I told you at that time that the creep is the first phenomena which people looked at for developing constitutive equation. Similarly, this map idea also started from the creep deformation only. Okay. So, already we have discussed in creep that you have a dislocation creep, you have diffusional creep. Diffusional creep also we have Harper, your Navarro Hering creep, NH creep, or you have Coble creep. Okay. NH creep is dependent on the diffusion through lattice, okay, whereas Coble creep is dependent on the diffusion through grain boundaries. So, you have these different type of creep processes. So, I want to know that okay, we at which temperature stress condition, which particular process will be the dominant process. Okay. So, M.F. Ashby was the first guy who proposed this kind of maps, and they used to call it as deformation mechanism map. Okay. that what mechanism, which deformation mechanism is operating at a particular temperature stress condition, okay, that they are trying to identify on a map. And the deformation mechanism maps were plotted on a graph, okay, where you have normalized stress and homologous temperature. Okay. I do not know whether I have told you homologous temperatures, if I express the temperature in this form, okay, the deformation temperature is divided by the melting point or temperature of melting of that particular material. So, you are actually normalizing it. Okay. So, when you do something like this, it is called homologous temperature. And what maps show? Maps show area of dominance of a particular creep mechanism. Okay. So, in particular area which mechanism is dominating, that the map will be able to tell you. Okay. So, this map will look something like this, okay, where you on the x axis you have homologous temperature T by Tm. So, now you can say see it is from 0 to 1 obviously. So, all the different materials can be clubbed together when you do something like this, and on the y axis you have stress, okay, which is normalized by the shear modulus. Okay. On the top you can see this is my theoretical strength. Okay. So, if you have done in your mechanical behavior course or strength of material course, okay, theoretical strength you can calculate for a material, okay, which is usually scales with the shear modulus. Okay. So, if you see the usually I am just putting a parameter some number here. Okay. So, usually it is in this range G by 10, okay, the shear modulus divided by 10, that will be your theoretical strength. Okay. So, that is my line 10 to the power minus 1, okay, because G by 10 is normalized by G. Okay. So, it will be 10 to the power minus 1. Okay. Then there are different mechanisms, as you can see, are identified here. Okay. So, this is the higher strain rate, lower temperature. Okay. You can see higher strain rates, lower temperatures. Okay. So, temperature is going down here and stress is going up here. Okay. You can see that dislocation glide, which is the normally deformation mechanism at lower temperature, will dominate, okay, up to a certain temperature. Okay. So, from very low temperature to a certain temperature, your dislocation glide is the deformation mechanism. Okay. As you go to lower strain rate and higher temperatures, okay. So, in this case now you are going to lower stresses and higher temperatures. Okay. As you are going there, you will see that the creep deformation is starting to dominate, okay, and in that also you have different type of creep mechanism. Okay. In this region you have a dislocation creep, okay, this is your low temperature creep, okay, and this is your HT is your high temperature creep, okay, through diffusion mechanism, and somewhere here you have a dislocation creep mechanism. Okay. As you go to even lower strain rates, okay, and of course, still at higher temperatures, your diffusional creep will start dominating. Okay. As you can see at lower stresses, the Coble creep, which is a grain boundary diffusion process, and NH creep, which is the lattice diffusion. So, lattice diffusion will obviously be even at higher temperature, because you for lattice diffusion you need vacancies, okay, and vacancy concentration increases exponentially with temperature. Okay. So, you need more vacancies for diffusion. So, grain boundaries already have lot of because of the disorder, you have lot of open area where the diffusion can take place very easily without creation of vacancies. So, that dominates at lower temperature. At higher temperature, when the vacancy concentration increases exponentially, you start having the lattice diffusion. So, you can see that as you are going to lower stresses, higher temperature, diffusional creep is taking place. Still higher temperature, but slightly higher stresses, you will start having dislocation creep. Okay. Even higher lower temperature and higher stresses, you will have dislocation glide. Okay. So, you can see that all the different mechanisms are nicely shown on a single map. Okay. So, what these regions are doing is, from the map we can read of the dominant deformation mechanism as we are doing it, and these boundaries, okay, between two deformation mechanisms are obtained by equating pairs of constitutive equations. Again you can see that constitutive equations are coming here. So, you have one constitutive equation for NH creep, we have already seen that. We have one constitutive equation for Koebel creep. Okay. So, you will see that when the strain rate predicted by these two constitutive equations, okay, when they have equal contribution, okay, the strain rates are matching for both these processes, there we will say that a boundary is there between the two. So, at the boundary you have equal contribution from Koebel creep and NH creep. Okay. So, strain rates are same for both the constitutive equation, from both the constitutive equation, but as you go to higher temperatures you will start seeing that the strain rate predicted by NH creep is higher than the strain rate predicted by Koebel creep, whereas if you go to lower temperature, strain rate predicted by Koebel creep is higher than the strain rate predicted by the NH creep. So, that is how you can have the demarcation between the two processes. Okay. So, again you can see that constitutive equations are used to demarcate the region, okay, and of course, this kind of demarcation will be highly dependent on the accuracy of your constitutive equation. Okay. So, obviously at these boundaries, okay, where two different mechanisms are operating, okay, their contribution will be equal to the strain rate. Okay. So, this is what I was trying to tell you. So, I can easily read out the deformation mechanism, okay, and I can easily find out that which deformation mechanism is operating in which particular area. Now, there was another addition to this deformation mechanism map. Okay. They started also superimposing the strain rate on these maps. Okay. So, you can see that the strain rates are very low for lower stresses, okay. But as you are increasing the temperature, the strain rates are going towards higher values. Okay. So, this is if you are not able to see, this is 10 to the power minus 10, 10 to the power minus 9, 10 to the power minus 8, and as you can see that as I am increasing the applied stress, the strain rate is increasing. So, this is 1 per second here. Okay. So, strain rates are increasing. So, these strain rates are superimposed on the deformation mechanism map. Okay. So, and of course, these are also plotted using only all the constitutive equations. Okay. So, constitutive equation for different regions were used to develop these strain rate contours. You can see the effect of different deformation mechanism also. So, wherever the boundary is, there is a change in the slope of this strain rate contours. Okay. You can see there is a sharp change here. Okay. Similarly, a sharp change here. Okay. So, wherever there is a change in the deformation mechanism, you see a change in the slope of this constant strain rate contours also. Okay. Now, what is the effect of grain size? Okay. You can also see very nicely that how the grain size affect the deformation mechanism map. Okay. So, this is for 1 micron, these are all for FCC nickel. Nickel is an FCC material, pure nickel. Okay. And so, this is for 1 micron, this is 10 micron, 0.1 mm means 100 micron, and 1000 micron 1 mm. Okay. So, grain size is increasing in this direction. So, how it affects the deformation mechanism map? Okay. You can see that when I have if I compare with the two extreme one right now, okay, you can see this is 1 micron and the boundary diffusion is the only one I am seeing in the diffusional flow. Okay. And the power law creep, okay, power law means where the stress or strain rate is dependent with some stress exponent. Okay. So, the equation will be something like this, or I think we used C there to the power n or m prime, let us say. Okay. So, there is a power law dependence. Okay. So, you have a power law creep okay, in that you have low temperature creep and high temperature creep, okay, and then you have diffusional flow, okay, and in diffusional flow only the boundary diffusion can be seen in this particular map. Okay. For the same nickel, okay, of course, all the temperature restraint rate are same because these are all normalized. If I see for 1 mm, that is 1000 micron, I can see the lattice diffusion also here, okay, in diffusional flow, okay, and also the grain boundary diffusion is almost there is no region for grain boundary diffusion. That means, as I told you that Kowal creep dominates in the material with finer grain size because you will have more grain boundary area. So, grain boundary diffusion will be more obviously, okay, whereas NH creep, okay, that dominates in the coarse grain material because their grain boundaries are less, okay. So, only the diffusion can take place through the lattice, okay. So, you can see that the lattice diffusion field is coming here, which is almost absent here, and here grain boundary diffusion is absent. But if you see, let us say for 0.1 mm, I can see both the lattice and the grain boundary diffusion in the diffusional flow where the diffusional creep is taking place, and also the size of the power law creep area is increasing. Okay. Here it was very less in the fine grain size material, but in coarse grain material the power law creep is extending up to a stress of I think 10 to the power minus 5. This is 10 to the power minus 5, okay, almost going up to there, whereas in this case it is almost ending at 10 to the power minus between 10 to the power minus 4 to 10 to the power minus 3, okay, and it is also shifting towards the lower temperatures. Okay. At lower temperature you can start having the creep process. Okay. So, very interesting that to see the effect of microstructure on the deformation mechanism map. Okay. Of course, you should be seeing that it is only developed for pure nickel here. Okay. So, this is the effect of grain size. Okay. So, as grain size is increasing, you are having lattice diffusion is coming as one of the field. Okay. Also, my power law creep area is increasing, okay, in this direction. Now, this is the difference between the two different crystal structure. Okay. So, you have one tungsten which is BCC here, okay, whereas this is pure nickel, this is FCC. Okay. Just to, and again because I am normalizing with their melting point. So, I can easily compare between two deformation mechanism. Okay. This is also normalized the stress, similarly temperature is also normalized. Okay. So, I can compare between the two. Okay. So, one thing you can see that at lower temperature my yield stress is dependent on the temperature. You can see that there is a sharp slope here, okay, at lower temperatures. Okay. This is because of the lattice resistance to dislocation movement, pulse stress. Okay. Whereas in FCC material you do not see a very strong dependence, okay, very shallow slope is there, whereas in this case it was a very sharp slope. Okay. So, in BCC material there is a strong temperature dependence on the flow stress or the yield stress of the material. Okay. If you come to higher temperatures, okay, again you have a power law creep region, okay, where you have low temperature and high temperature region. So, the area of power law creep is over a one order of magnitude difference is there between the strain rate. Okay. Here also almost it is one power of one order of magnitude difference is there. Okay. The interesting part here is about the diffusional flow. Okay. You can see boundary diffusion as well as lattice diffusion in the BCC material, okay, and lattice diffusion is starting after homologous temperature of maybe around 0.78 or so, whereas in this case you do not see any lattice diffusion. Okay. This is actually the lattice diffusion which is hardly having any field here. Okay. the whole thing is boundary diffusion at 10 micron. Okay. That means there is something in the crystal structure, and why BCC has more diffusion through lattice is because it has more open structure. So, diffusion through lattice is much easier in case of BCC than an FCC material. FCC is a more compact atomic arrangement. Okay, so that effect you can see here. Also, you can see that there is one region of dynamic recrystallization is also shown here. Another interesting thing is that you can see this constant strain rate contours. Okay. So, in case of FCC material, it is going 10 to the power minus 10 is going up to 0.4 homologous temperature, whereas in case of BCC material, it is going only up to 0.5 homologous temperature. So, there is effect on the response of the material also as you are changing the crystal structure. Okay. So, the mechanism map will change also as a function of microstructure, grain size we have just seen, and also as a function of the crystal structure. Okay. Some more modifications were tried on deformation mechanism map. Okay. A very good source if you want on deformation mechanism map is this particular site. Okay. You can go through this site also, that you can superimpose the forming operation on a deformation mechanism map. Okay. So, you can see they have superimposed a forming operation like cold working. So, explosive deformation, very high strain rate, okay, at low temperature, then wire drawing, okay, another low temperature deformation. So, all these are being done at lower temperatures. Okay. Then machining, this is all machining also can be considered as one of the deformation process only. So, by deformation only you take out the chip. Okay. Then you are coming to warm working here. Okay. That means temperatures are increasing. Similarly, hot working is there. So, these strain rates are more than the creep deformation. Okay. Temperatures are high, but the strain rate or the flow stress if you see here is more here. Okay. Whereas, the creep takes place at lower stresses. Okay. And if you come to creep, you have power law creep. Okay. Of course, there is a power law breakdown also. So, after certain strain rate or stress, there will be a power law breakdown. We have seen that power law equation was only valid up to a particular strain rate or stress range. After that, it was not a power law. We used an exponential equation for higher stresses. Okay. So, you can see there is a power law breakdown here. Okay. Below that it is power law creep, and even below that it is a diffusional creep. Okay. So, the material which is used for high temperature structures, they are used in this range, okay, where only the diffusional flow will be the important one. That means, the stresses on the components are much lower, okay, so that the other deformation mechanism should not operate. Only diffusional flow you cannot stop if you are working on at a higher temperature, at temperatures more than 0.5 Tm. Okay, but still you can see the strain rates are very low. The strain rate contours are 10 to the power minus 14 to 10 to the power minus 12 in that region. Okay, you will use the material for structural applications. So, for example, a thermal power plant, the material which are used in thermal power plant, or in a gas turbine, the material is used in gas turbine. So, what will be the temperature that material will be used in those structural application? That particular region is this one, whereas deformation, warm working, hot working will be in this region. Okay. Cold working will be even at lower temperature and higher stresses. So, they were also trying to superimpose the deformation processes on the processing on this deformation mechanism map, but again please be careful, we are doing it for pure copper. Okay. Now, there was another extension to this idea of deformation mechanism map, which was proposed by Ashby. Okay. You can see that only the the stable behaviors are shown there. For example, only where there are no defects are identified in their processing map. Okay. So, R. Raj, another researcher, extended this concept of HB by including the defects or damage mechanism also in the deformation mechanism maps. Okay. For example, he introduced the idea of cavity formation during the deformation. At high temperature, cavity formation is a very important defect which can takes place. So, this cavity forms at hard particle which are embedded in a soft matrix, or there can be a wedge cracking at the grain boundary. Okay. Grain boundary becomes weak at high temperature. So, grain boundary separation can takes place. Okay. So, these different microstructural phenomena can be, which are related to defect, can be superimposed on the processing map or deformation mechanism map. Okay. So, this was an extension to that idea. Okay. So, this is what they were trying to bring out. So, you have strain rate on the y axis and temperature on the x axis. Okay. So, different defects are identified, for example, wedge cracking, okay, a ductile fracture. Of course, at low temperature at sufficiently high strain rate you will have a ductile failure. Very high strain rate, as I have already told you, that you can have adiabatic heating, okay, because you are not giving enough time for heat to dissipate. So, again you can see around strain rate of 1, above that the adiabatic heating will start dominating, or it will be an important factor. Okay. And we also did stress correction in the constitutive analysis only above the strain rate of 1. Then you can have dynamic recrystallization, which is the desired microstructural change, okay, which will be at higher temperature and sufficiently at intermediate strain rate range. Okay. So, you have failure at different level, and this is my safe region. The dashed area is the safe region for my processing, where you won't introduce any defects. Okay. So, there are couple of schematic is shown for the formation of cavity. So, this is my hard particle in a soft matrix. Okay. So, when you are deforming, what will happen? The deformation, because matrix is soft, it will be able to deform, but the particle is hard, it is not going to deform. Okay. So, because of that there will be the interface between the particle and matrix will have a breakdown, okay, and you will create cavities on both the side of the particle. So, that can happen as one of the defect. Another one is this wedge. Okay. So, wedge is a shape like this. This is a wedge. Okay. So, when you want to create for example, in when you are cutting wood, okay, you put a wedge and then you hammer it. Okay. So, wood will open up. So, this is what you can see, a shape of a wedge here on the grain boundary, and that happens because of the separation of the grain boundary. So, you can see it happens at very high temperature, but relatively lower strain rates or lower stresses. Okay. So, at high temperature the grain boundaries become weak, and even a small stress will be able to separate the two grains at the grain boundary, and you will have a defect called wedge cracking. Okay. So, these are the different defects he superimposed on the deformation mechanism map. Okay. Now, the problem with deformation mechanism map is that you have to have a very good understanding of the atomistic processes. Okay. Like what is the creep, where the creep is taking place, diffusional creep, dislocation creep. So, you have to for every processing condition you have to do a very good microstructural analysis, and you have to have a very good understanding of the microstructures, okay, to understand that what type of process is taking place. Okay. So, you have to have a very good knowledge of all these microstructural changes. Okay. And again, for a practicing engineer, doing all these things will be too much to ask, because he has to also look at the production. And also, as I have told you at different places, that these maps were developed only for very simple system, pure materials, pure copper, pure nickel and so on, okay. Because there only you can ascribe or you can attribute a certain deformation mechanism for a particular microstructural change, okay. Whereas, if you have a complex material, you have two phases, you have precipitate, you have solute solute atoms, then clearly identifying that which particular constituent is responsible for a particular mechanism is very difficult, okay. So, for complex system, it is difficult to attribute deformation due to one single process, because there are multiple processes taking place. Dislocation is also there, diffusion is also taking place, solutes are diffusing, okay, and precipitates are doing their own business, okay. So, these deformation mechanism maps are very useful to understand or to develop the understanding, okay, but it will be very difficult to apply it to main engineering alloys, okay. And also it will be very difficult to predict any processing conditions from these maps, okay, for processing of a complex alloy, okay. So, we will come to the next lecture, that how it was solved, okay, that this deformation mechanism map idea was extended, okay, and how these particular problems were solved in the processing map, which is used for hot deformation processes, okay. So, thank you for your attention.